Come back. Conflict resolution in master-master replication. So, in master-master replication, conflict resolution is one of the most challenging aspects because multi-masters can write to the same data simultaneously, leading to data conflicts. These conflicts occur when two or more masters update the same piece of data independently. To ensure data consistency across all nodes, you must have a strategy to detect and resolve these conflicts. There are several methods for solving conflicts resolutions in master-master replication, each one with its pros and cons. The best solution depends on the application requirements, such as how critical it is to prevent data loss, maintain consistency, or achieve high availability. Today, we will talk about two things, but let's just make a small recap if you don't know what is a master-master database. A master database, uh, data it's an architecture that helps the system be available, and also it helps in increase the right scalability, because every database or every the architecture has more than one master. So and the master, as you know, supports right. And in the master database, let's assume we have two nodes, and these nodes support read and writes both. And when the server writes something to master db2, it will be replicated or copied to master db1. And write operations mean that we could insert an item, update an item, or delete an item. So let's say that the server, there is another server. No, it's not a good server. Let's say that there is a good server and another server here called server one, and it tried to update a user with the ID uh, 4. It tried to update its name to be, for example, Tom. Okay, and in the same time, server 2 is trying to update the same user, and it try to update its name to be Muhammad or Mo. So right now we have a conflict. We have a conflict right now, and we need to resolve this conflict because server 2 updated the user with ID 4 to be Mo, and server 1 updated user 4 to be Tom. So in order to solve this one, there is multiple ways to solve it. We can discuss the first one, which is the lost. Oh no, this is too big. Lost write wins. So in this approach, the system uses timestamps to track when a piece of data was last updated when a conflict occurs. The version with the least timestamp is considered the correct version, and all other versions are discarded. So the system will look about, okay, which one was the last, was the request from server 2 or server 1. If server 2 was the last, so the name of user 4 will be Mo. If server 1 was the last, that the name was the name of user 4 will be Tom. So let's try to discuss again how it works. Let me no, can I go back? Yeah. Let me just try to remove everything here, and let's say that we have server 1 and server 2. Okay, so each master node includes a timestamp with every write operation. So When server 2 trying to make a write operation, it will have a timestamp in it. When server 2 trying to have a write operation, it will have a timestamp with it. So if we have two or more nodes update the same data, the system compares the timestamps of the conflicting updates, and the updates with the latest or the latest timestamp wins, and other changes are discarded. The pros of this one, the simple white wins, it's simple to implement and works well when the system does not require strong guarantees about which updates is retained. The cons of this one, it has, I would say, it has mainly two things. The first thing, the risk of data loss, because let's say that if server one changed the user ID to Mo, and server 2 changed the user ID to be Tom, and server 1 was the last, so it will win, and number 2, server 2 changes will not be its username, so we right now might lose the data. So the changes made by one node might be overwritten by a later update or from other nodes, even if the real update was important. And this one can lead to data inconsistencies if clocks on different nodes are not synchronized correctly. The use case of the last write wins, it's suitable for applications where occasional data loss is acceptable, such as user preference settings or cache systems. There is another way to solve it, which is the version vector clock. Mm. Okay. So a version vector or vector clock is data structure that tracks the history of changes made to a piece of data by different masters. This allows the system to detect and resolve conflicts by understanding the causal relationship between different versions of the data. So let's talk about how this works. So each replica, let's say that um, server 1 updated the user which ID4 to the master DB2 to be Mo, and user server 2 updated the master DB2 user with ID4 to be Tom. So right now we have two names to the same user. So a vector, so each replica maintain a version vector that records the version number for every other replica. So when a conflict occurs, the version vectors are compared to determine which version happened before another, version happened before another. So this enables the system to merge or discard conflicting changes based on their causality. So when DB master 2 try to replicate the user with ID4 with Mo, it will update it, but also it will put the version of which master. So we will have like the user will equals the user name will maybe have two versions because it has a Tom version or more version. The pros of this one, it allows for conflict detection and resolution without arbitrary decisions like timestamps. It helps maintaining consistency by tracking the entire history of updates. The cons of the vector clocks is that the complexity, because the complexity increases as the number of replicas grows, and version vectors can become large. Conflict resolution can be more computational, expensive due to the need to compare vectors' history or version histories. The use case for this one is useful in distributed systems where you need to maintain the order of changes and resolve conflicts based on causality, such as distributed databases or multi-region applications. There is another solution, which is the conflict-free replicated data types, which is called as a CRDT. And the RDT are a special data structure designed for distributed systems that can automatically resolve conflicts based on predefined rules. These structures ensure that all replica eventually coverage to the same state without any need for manual conflict resolutions. We can look about how this works. So the CRDTs allow multiple updates by to be merged without conflicts, even when updates happen concurrently. So an example for the let's say the example of CRDTs include counters, like when you increment and decrement are additive, like sets where elements can be added or removed in a conflict-free way, and register that can store values with a conflict resolution rules. So it's a pros of this one. It's automatically resolved conflicts without data loss. Number two, it ensures eventual consistency and allows for concurrent updates. The problem with the CRDTs is the complex to implement and requires that application logic be compatible with the RTTs. It's not suitable for every type of data. It's like complex relationships between entries or non-competitive operations. It's ideal for applications that require concurrent updates without data loss, such as collaborative editing systems like Google Docs or real-time analytics. So let's try to think about this one. So yeah, the conflict resolution in master-master replication is a challenging aspect of designing distributed systems, but with the right strategies, it can be effectively managed. Each method has trade-offs in terms of simplicity, performance, and data integrity. So it's crucial to choose conflict resolutions, the conflict a conflict resolution approach that aligns with your application requirements. So, for example, the last right wins. It's simple but can lead to data loss. The CRDTs are more complex but ensure eventual consistency without conflicts. The version clocks, it's ensure that no data is lost at all, but it's really conflict. It's really complex. And by carefully selecting and implementing the appropriate conflict resolution strategy, you can ensure that your master-master replication system remain consistent, scalable, and performant, even in the face of concurrent updates from multiple masters. So that's it for this video, and see you in the future.